thin cylindrical shells. So it's round, it's not flat. All right? Okay? So that's a strategy. And so here is the deal. You have, to begin with, this curve over here, which is y equal to 2x squared minus x cubed. So let me do a very rough sketch. It's like this. Go up, and then go down to hit the x-axis again. Right here. And at 2, if you plug in 2, this is a minus a is 0. So it does mean the x-axis is over there. And then you go to 2, right? So this is from 0 to 2. Then I'm going to rotate this one around the y-axis. Then what's the object that you build? Can you imagine that? It's a little bit like, I don't know, it's a little bit like the container that you use to feed your dog. Does it look like this? Right? Can you imagine? Right? Right? Okay. So, you know, it's going to build something like this, and it's like a ball. Okay? All right. And so this is still, you know, region resulting from a revolution around an axis, right, a line. That's good. So this axis, y-axis over here is the axis of rotation. Now, this time, as I said, I'm not going to slide this way. And so what I'm going to do is still, I take this mass, you know, and then I'm going to cut it into pieces. But each piece is not flat. Each piece is a cylindrical shell, very thin cylindrical shell. So how do I manage it? I'm gonna start with this region R here, and then I imagine that I divide it up into a lot of vertical pieces like this. Can you imagine that? Okay? Then I single out one of them, which is very thin, Then, as I do the rotation, right, just this slice alone is going to generate what? It's going to generate some very thin shell, cylindrical shell. Are you with me? Okay? So I'm gonna imagine that I'm sweeping that one around the y-axis. Then it's going to generate something like this. Are you with me? Everybody understand what I'm doing here? You know, so you have, you know, something which has certain thickness. It's a cylindrical shell, and the part that you can't see is this. So it's you know, it is a little bit like if you were to cut it and then try to flatten it, then you'll get something that resembles a rectangular, you know, thin plate. Which, if you then, you know, close up again, right? Then you can reassemble the cylindrical shell. So each of this original vertical slice is going to generate such a cylindrical, you know, shell, which carries a certain tiny volume. Then I do that for each of these little vertical pieces, right? Each one of them generates a very thin cylindrical shell. Then if I assemble all these shells together, wouldn't that be what I have originally? Is that right? And so if I want the total volume of the material needed to build that bowl for your dog, then what I have to do is to add up all the volumes of these tiny, not tiny, but very thin cylindrical shells. So that's the game plan. Got it? So it's divided up not into flat pieces, but into cylindrical, very thin cylindrical shells before you assemble them together. And so ultimately, the formulation is some sort of integral, which is some sort of a sum anyway. So it's going to be like this. Integral. And so this is a sum of a lot of cylindrical shell. And I want to have a quantity to control the process. You see that over here, I have a smaller shell, and then gradually the radius gets bigger and bigger. It's still very thin, but the radius is bigger and bigger. Is that right? So start from the 0 until the largest radius possible is about 2. Right? And therefore, I'm going to use x as my controlling variable. Just from the smallest radius, which is when x is equal to 0, to the largest one, that is when x is equal to 2. And here comes the generic one, at what is called x. Now, what is this curve here? This curve here is this curve, correct? So if this point is x, what is this one? That would be y. Is that right? So what is that y? Y is 2x squared minus x cubed. Now, here comes something that you have to convince yourself of. Here is a typical cylindrical shell, like this. Right? Okay. What's the volume of this one? Must be very small because what? It is very thick, right? And then roughly speaking, it can approximate it by, as I said, you cut it and try to flatten it. And then you will get something like a rectangular piece with certain thickness, right? And so what is the height of that rectangle? That will be the height of the cylinder, right? And what is the width of that rectangle? Wouldn't that be the perimeter of this circle? Right? So now here is the radius, r. If you take r multiplied by 2 pi, what is that?
Diameter.
That's perimeter. Is that right? And that perimeter then becomes the width of that rectangular sheet, right? And then the height of that rectangular sheet is just the height of this. So this one is, I call it h. So that's h. So this width times height, that is the area of that rectangular sheet. But that sheet has a thickness. And that thickness is the same as this thickness, right? So I better multiply by what? What I call the delta R. Delta R is like, this is delta, this symbol means this thickness, delta R. So I thicken it. Okay, so this is something that you want to keep in mind. And it is very small precisely because delta R is very small. In the book, there is a more careful derivation of this, which I reproduce here. If you don't want to think this in terms of cutting it and flattening it out into a rectangular sheet. Then you can instead do it this way. There are two radius, and they are very close to each other. The difference between the two is delta r, right? So I have a smaller one, which I call R1, and the larger one, which is called R2. And then you consider a solid cylindrical mass of height h and radius r2. And that will be pi r2 squared times h, correct? And then that one includes a shell and everything in it. But what you're going to do is to remove, the things in it so that you're left with just a shell. So the thing that you have to remove itself is cylindrical as well, and that is pi r1 squared times h, correct? And so if you manipulate it, this becomes pi h times what? R2 squared minus R1 squared. Can you factor this? What is that? Pi h and then what? R2 plus R1, R2
minus R1.
minus R1. And then these two are roughly equal, is that right? Because the difference is only delta r, very small, right? So if you take the average, this is roughly 2r, where the r is sort of the average of the two. Okay? So 2 times the average. So that's r, the rough radius of the thing. That's called r. And 2r, that is really the sum of r1 and r2. What is this piece? 0. Delta r. It's a tiny difference. And therefore, I reproduce which formula? This formula. 2 pi r h delta r. 2 pi r h delta r. So this is a little bit more careful derivation. But I mean, the first approach is, would suffice. Just imagine that you cut it and unfold it to get a rectangular piece. All right. So I'm going to implement it. So I'm going to assemble a lot of, all these cylindrical shells together. Each one of them has a little volume, right? And what is that volume? That volume should be, the volume of this one, for example, is a typical one. And what I have to do is to take 2 pi